Yeah. So I'm Bhuvaneshwari. Yeah, so I'm Bhuvaneshwari, and I'm pretty new to this topic as well. It's just that I was introduced to this fairly recently, and I was introduced to Python also like hardly 1 year ago. Like I properly started working on Python. But then when I started working on this, I couldn't. It just blew my mind away that there was so much going on. Like this is such a fastly progressing field, and there's so much active work going on, and it's just people are just working on, building on, and it's such a very nicely collaborative field, and it was just amazing to just be part of it. So I just thought it was a nice thing to just help just put this across in this forum, and you guys can also know about this. And if anyone of you is interested, you could just maybe this might be a good starting point. So just introduction. But as with any introduction, first history. Okay, so this is an image which is fairly 50 years old, but this is the starting point for all the computer vision thing that happened. So there were these two scientists, okay, David Hubel and Thorsten Weisel. I don't know if the pronunciation is correct. So what they did is they wrote a paper called Receptive Fields of Single Neurons in the Cat's Striate Cortex. And I do not have any idea what that means, but that's the name of the paper. So what they wanted to do was, they wanted to find out, they wanted to analyze the brain of a cat and see if, how it responded to images. So they wanted to find out, they were presenting slides of images in front of the cat, and they were trying to stick rods into its head and just find out, which neurons are activating for what images. So they found that when the images are moving for different images, they couldn't really make sense. Like this image, when I show it repeatedly, the same parts did not activate. So it was not like one image was activating one area. But then what they found out was, as the slide kept moving, so it sort of moves like this, it's scoops across. So when it was moving, those are like glass slide projectors, and it casts a shadow, and there was a line similar to that, which kept repeating, like every time they moved the picture. So whenever that line came about, there was one particular neuron getting activated. So this led them into thinking that, okay fine, it's not that the brain cells are getting excited by an overall image, but it's just that one particular edge, that one particular slide being moved across, that one line was exciting a particular neuron, and that is what is sort of making the images. So they sort of classified, they said that, okay fine, there are simple cells, there are simple neurons, and then there are complex neurons, and those make up your brain, those make up the neurons in your brain. So it's not as simple as just one. So you can't say that a whole image. It's like simple neurons tell you that, okay, this is an edge, this is a dot, this is a curve, and all that. And the complex neurons, they process the information from this and say that, okay fine, these two edges go together to make this more complex shape, and they join together, and it's a progressive step. It starts from one simple thing, which could be, an edge. So then, next part of history is that this guy, Russell Kirsch, invented a first digital image scanner. That was the computer which was used to scan the image. It was that huge because it was in 1957. It was a drum scanner, basically, which means there was a drum on which an image, a photograph of this baby, his kid, was there. And they scanned this image, and this was the first digital image to be there. So digital image means image was now represented in terms of bits, in terms of numbers. So before that it was all analog. So now this was the scanner. So this sort of was a step in computer vision. So you could take numbers from images and process them. So then came this. There was another guy, Lawrence Roberts. Lawrence Roberts is more commonly known for inventing the routing aspects in ARPANET, which is the internet came from ARPANET. So he did that one. Before that he wrote a paper on how to convert 2D images to 3D models. So he said that, okay, you can take 2D images, you can find out edges and stuff like that, and you can make 3D models into that. And then there was another guy who wrote a paper, and he again said that vision is hierarchical. So basically the point of all this history is that all of these people came to a conclusion. They were building upon each other's findings that, it's not about an entire picture, but it's about small things, and they all sort of collate into a So, okay, so I think this is getting a bit long still. So this lady, Kunihiko Fukushima, she built this neobarbiton, which was the first artificial neural network, okay? And she built this with layers. So you could, like, equating it with the simple and complex cells that I was talking about. So you could see that there was one layer which is doing the function of a simple cell, and the next which is doing the function of a complex neuron, and similarly. So there were these things stacked up. So she built this artificial neural network which had these simple and complex cells, and it was able to recognize patterns. Okay, it was able to recognize basically numbers from handwritten digits. And this guy, Jan LeCun, is the father of neural networks as is today. And so the previous lady, Kunihiko Fukushima, is actually the grandmother in some aspects. But what he did was, this is his design of a convolution neural network. So at this point, what has happened is, the concepts had stopped with this. The concepts were that you had to take, like small elements and then build above them. Over here, the variation is more of the number of layers and how do you arrange the layers and how do you make sense of them. That is what has changed in here and here. So he has, this Jan LeCun came up with the idea that he will use a 28 into 28 convolution and this. So this is the architecture he proposed. When I explain the next thing, you'll actually understand this a bit more. So, finally, what happens when you say convolution? So basically, first there was when you say, okay, consider this is an image. So you have a 4x4 image. So what you do is you need to now extract features from this image. Let's say you need to extract if there is an edge, or if there is a some curve, or if there is a dot, or if there is a circle or something. You want to extract that. So you have a feature extractor, which is a kernel. So it can be, you can call it a kernel, you can call it a feature extractor. It's completely terminology. So what happens is that scans over your image, and then it sort of gives you an output matrix. So that's a matrix, and that's a like a feature extractor matrix, and then you have your output matrix. So you get the result, and with that result you apply more convolution layers. So basically what happens is, all the information from that image is being condensed, and it is being progressed through various layers. So from that it goes to your second layer, which is just a bit smaller, and then the next layer will be a bit smaller. Here it's actually bigger because that's actually a much bigger image, and we just picture sections of it. So you have multiple convolution layers which go across doing this. So now I might be a bit here and there and confusing. So you'll get that there's a video which comes in which will
Why is it called convolution?
Why is it called convolution? Is actually a mathematical function. Okay. So what it does is it is just combining two signals. So it's convolving two signals. The two signals here are nothing but that's your image, and then whatever this is your feature extractor. So those two signals are being combined. So this is nothing but a set of weights. So for that you have a 2 into 2 matrix of weights. So you're combining those two. So it's nothing but multiplying and adding them. So I will give an example of convolution just So the point is that you have a whole image, and then you convolve over the image using this feature extractor. The feature extractor is a kernel, and the kernel is right now just based on experimentation. Different people just experimented with different size of kernels, and they came up with 3x3 is an ideal size. So what they did is, okay, make a 3x3 kernel and convolve over an image, which basically means you take 3x3, which is 9 weights. Initially randomly assign 9 weights, and you convolve over the image. The image is nothing but a matrix of digits. It's a matrix of numbers, whatever the pixel values you have. So when you convolve over it, you get an output image, which is like that. So that's a 5x5. You get an output of 3x3. When you again convolve, you get 1x1. Because when you take a 3x3 region, you see that this has information from all that. The previous thing, you see, this is how convolution happens. So that section goes to that cell, and the next 3 cross 3 section moves to the second cell. So the information carries on to the next layer like that. So when you know that all the information gets condensed, in a 3 cross 3 you lose like dimensionality by just 2. So yeah, you reach this point, and then how you can visualize it is that the information from all that is there in just one pixel now. But why it is all being done, I'll just get to it, but there has to be some context before that happens. So if any time, if you just want to clarify on something, just please ask. I don't know. So, and max pooling is another concept. Right now, it's just know that there is max pooling, but I'm just stating a lot of concepts right now. I will stream it into a proper sequence in some time. Just max pooling, what it does is, so this you can just think of this in this way. This is a slow progression. So when you take a huge image, let's say 256 into 256, it's not really huge, but in terms of this progression, 256 into 256 if you take it, and if you're going to progress on it this way, revolving over 3 cross 3. So the time it takes for you to reach a 10 cross 10, so many layers, it takes so much time. So intermediately, what you do is you apply a max pooling layer. So what that max pooling does is, it takes a whole section, a particular size, and it just takes the maximum value. Usually, the norm is to take a 2 cross 2 area and just so ultimately your whole image will be halved. So you just get the maximum. Pixel maximum value will be taken and it will be assigned to the next layer. Instead of doing the weighted convolution, you do a max pooling, which will take the maximum value. So in a weighted convolution, you convolve over that area. When you say convolve, you mean you multiply. You basically do a matrix multiplication with this one, and then you get the result of it and you assign it to the pixel in the next layer. In terms of max pooling, you're not doing multiplication or anything. You're just taking the maximum value and you're putting it to the next layer.
So, I have a question. So, these two things, these are you can either do convolution or you can do max
pooling. So, when you have an image, you can process it. So, image, when you're thinking about neural networks, you're supposed to think of it in terms of it's a matrix. It's a matrix with numbers. So that's why the digital scanner was important, because before that you couldn't get a matrix of numbers from images. So with a matrix of numbers, you can do any operation. You can do a matrix multiplication, you can do transposition, you can do all those things. So all those things you can do. Using all those techniques, what and all you can do, how and all the image can be processed. That's the whole, that's the whole question in the computer vision field.
So how do you decide which step you want to do, whether you want to do the matrix multiplication
yes.
or max pooling?
So basically right now how it is going is it's a whole lot of it is experimentation. So if you see the Jan LeCun's model which was there over here. So what he did is he said that use convolution there, then use max pooling, then use convolution, then use max pooling. So that was his view. And he came up with a certain accuracy in the sequence. Some other people, and then he said that in the end, use 3 fully collected layers. So fully collected layer is another concept. So that is his architecture. So most of image processing and neural network comes down to the architecture of it all. So the basic building block concepts are your convolution and then your max pooling, and so it's basically how you arrange them, how you get the best output. So when you talk about convolution also, as I said, the kernel is 3 cross 3, and that has been arrived at after a lot of experimentation. People experimented with 5 cross 5, with 7 cross 7, 11 cross 11, and they said that okay, with 3 cross 3, if I convolve over an image, I tried with 3 cross 3, I tried with 5 cross 5, 3 cross 3 gave me the best accuracy. And this has been a lot of people have come up with this, and now we say that okay, 3 cross 3 is an industry norm. So we know based on experimentation. Similarly, if you see, there's one more concept actually which I can squeeze in over here. If you see over here, for this particular pixel, the first pixel, it has information from 3 cross 3 area in the first image. right? So then you can say that that pixel's receptive field is 3 cross 3. Similarly, you again add another convolution layer, which means that you do a 3 cross 3 convolution over here and you get 1 pixel. For this, the receptive field is actually 5 cross 5 because it has information from 5 cross 5 pixels in the first image, which is the whole image actually in this particular example. So now what people did is, again after a lot of experimentation, they came up with the fact that when you reach a receptive field of 11 cross 11, when you're processing any image and you reach a receptive field of 11 cross 11, you can do a max pooling. Because when you have 11 cross 11 information, you have enough information with you that you can reduce it, you can condense it, and you will still have a good accuracy. If you do it any sooner, it's like you'll be using more time and everything, but it's not going to give you too much accuracy. But if you do it any later, you might like lose information. So this is like a good 11 cross 11 is a safe bet. So now I'll show you my network, which I worked on like which I built, and that has like a excuse me. That has like layers and so that has layers like continuous 3 cross 3 layers, and when it reaches a receptive field of 11 cross 11, we do a max pooling. Then we keep doing 3 cross 3 convolution. Then we do a max pooling. When it goes so on, you like keep condensing the information, and then you get this thing. Now then again, there's
sorry. Okay, I had one more question. So these weights that you assign, so are these fixed or
no? So before what happened is before computer vision there was something, but I cannot go through all this thing. But anyhow, weights right now what we do with weights is that they are randomly assigned. Initially, you just randomly assign some random line values to the 3 cross 3 matrix, and it moves over, and you get all the you get a particular result. At the end of your network, you will have a result, and then you will see that okay, fine, this result is right or wrong. So there is something called backpropagation, which does your which basically there's a loss function involved, so it calculates your loss and feed forwards to the beginning state. So it will calculate how much loss is there. So it will say that okay, fine, this is wrong. So it will say that you have to apply this much variation to this particular weight. So the information moves back to the initial neuron, and the weights get adjusted. So initially you randomly initialize it, and as it moves forward, you take the first. So you do for a neural network, there's a training phase which happens, in which all these layers are there. You train it, you get the output. You say that okay, fine, this output is like not, it is varying this much from my expected output. So you have to retrain. So you do that's called epoch. So you run it for that. Epoch is nothing but iterations. So you say that okay, I did it for 5 times, which is 5 times run it through with calculating my loss, back propagating my loss. So then finally you will get your like ideal weights assigned. So every time you do a back propagation, your weights get modified, like by whatever the variation is there. It will get modified and it goes forward. So you randomly initialize weights, and then it goes forward, and then finally you end up after running a bunch of epochs, the weights get adjusted to the ideal. So yeah, I think so. All of this concepts. This video is actually quite a good. This is quite a good channel. It's called 3 Blue 1 Brown. So this video will do a much better thing of explaining, but not explaining.
We are at the cusp of disruption and a fourth generation of the industrial revolution.
This is a very good explanation, okay? But this has some obsolete concepts, like it has a fully connected network, but it's good for explanation, but it will give you a very good understanding of the concepts.
This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though there's also a couple layers in between called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons. And admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16, well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with the specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network, as an information processing mechanism, comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now, the network I'm showing here has already been trained to recognize digits, and let me show you what I mean by that. It means if you feed it an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents. And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now, in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road, because how would you recognize these subcomponents or even learn what the right subcomponents should be? And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in the digits 1 or 4 or 7, well, that's really just a long edge. Or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with very little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and the long vertical line, and those light up the neuron associated with the 9. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with a layered structure like this. Moreover, you can imagine how being able to detect edges and patterns like this would be really useful for other image recognition tasks. And even beyond image recognition, there are all sorts of intelligent things you might want to do that break down into layers of abstraction. Parsing speech, for example, involves taking raw audio and picking out distinct sounds, which combine to make certain syllables, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. But getting back to how any of this actually works, picture yourself right now designing how exactly the activations in one layer might determine the activations in the next. The goal is to have some mechanism to combine to edges, or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron in the second layer to pick up on whether or not the image has an edge in this region here. The question at hand is, what parameters should the network have? What dials and knobs should you be able to tweak so that it's expressive enough to potentially capture this pattern, or any other pixel pattern, or the pattern that several edges can make a loop, and other such things? Well, what we'll do is assign a weight to each one of the connections between our neuron